everybody online on this beautiful Friday afternoon. I know there is a large number of participants for today's lecture. There is a great energy and I want to welcome you all participants, colleagues and students. We have over 130 people watching online. My name is Stefan Lehmann and I'm a professor of architecture based in the United States. The Global Lecture Series Spring 2021 is a collaboration between the AIA Las Vegas, AIA Nevada, and the UNLV School of Architecture. Thank you to the American Institute of Architects and our sponsors. The series has 4 lectures and today is the final presentation of those 4. The lectures were by Snow Heta, who was our guest in February, Zaha Hadid Architects was our guest in March, and Renzo Piano Building Workshop, who was our guest last week. And today we have Transolar. I'm thrilled that our lecture today is by Transolar's partner, Professor Thomas Auer. As most of you will know, Transolar is a global consultancy and architectural engineering firm specialized on sustainable design, operating from offices in Stuttgart and Munich in Germany, in New York, and in Paris. Before I introduce Transolar and our speaker, I want to briefly mention the theme of the lecture series. The series of presentations explores the question of civic space, infrastructure, and sustainable public architecture, and the challenging role within cities in the post-pandemic era and the age of climate change of public space. A question that occupies architects and urbanists around the world. We know that we have a serious problem with climate change and the overall rise of global temperatures. The construction sector contributes around 40% of all the carbon dioxide emissions that lead to this warming. Therefore, architects can make a real positive difference. It is now my great pleasure to introduce Transolar Climate Engineering and Thomas Auer. Transolar are an international leading firm of climate engineers and architects working with some of the most famous designers worldwide. The firm was established in 1992, almost 30 years ago, next year 30 years, and is led by 6 partners, including our speaker, Thomas Auer. The practice permanently employs around 70 engineers and architects together with a further 10 support staff. Since its foundation, Transolar has been involved in the design of an impressive series of super green, energy-efficient buildings on a global stage, attracting a large group of followers. Transolar works at all scales in all sectors, developing sustainable design strategies for buildings and cities. In this role, Transolar has worked on high-profile projects, including with Herzog de Meuron, Stephen Hall, Jean Nouvel, Frank Gehry, OMA, Foster and Partners, and numerous others. Thomas Auer recently said in an interview, "Robust, low-tech systems are often the best solution and are based on common sense. Less technology is a good approach to apply only as much technology as really necessary." End of quote. Transolar says the aim of their work is to optimize energy performance and environmental quality, such as user comfort, while taking into consideration local specifics, including the climate, construction methods, and so on. We're going to hear about. Therefore, the project uses a range of different passive and active design strategies in combination with some carefully selected active systems to reduce CO2 emissions based on thoughtful research. So research-based design work. With each one of these projects, there is an enormous effort to combine research investigations for the selection of techniques, materials used, and there's always a focus on operational and embodied energy by looking at the entire life cycle of a project. Thomas Auer, our speaker, studied process engineering at the University of Stuttgart, where he graduated in 1994 and joined Transolar in the same year. He became a partner and subsequently managing director in 2000. The founder of the firm, Matthias Schuler, is a professor of environmental design at the GSD at Harvard University. Between 2001 and 2008, Thomas had a teaching assignment at Yale University, and subsequently he held visiting professorship positions at the École Spéciale in Paris, the University of Sassari in Italy, Ryerson University in Toronto. In 2014, he was appointed as chair of climate responsive design at the Technical University of Munich. He will first give an overall introduction of the specific Transolar philosophy and of his work, and then present selected projects to illustrate the different approaches. We are very honored to have Thomas with us. He's speaking tonight to us from Germany, where it's 10 p.m. Here it's 1 p.m., so 9 hours different. I hope you will enjoy the lecture, which is entitled High-Tech, Low-Tech, Robust, for 45-50 minutes, followed by 20 minutes Q&A. All participants are invited to send their questions via the chat box. Please use the chat box. Join me now in welcoming Transolar. We are super happy to have you with us. Over to you, Thomas.
Stefan, thank you very much. This was a very nice introduction. Let me share my screen. And I feel very flattered to, let's say, be able to speak in this series of these high-profile architects, particularly since we are an engineering firm and that we get invited from an architecture school and the, let's say, the architecture community in Nevada and in Las Vegas to speak about architecture from a sustainability, from an engineering perspective. I think it's an amazing and great honor. So thank you very much. And another thing I want to touch on, you mentioned about common sense. It was Aravena who wrote about Transolar in the Biennale in, when was it? I think in 2016. Something like Transolar is working or provides a high-end engineering on the service of common sense. And I found that this was the best quote I ever heard about our work, on the service of common sense, because I really think that we lost some common sense in architecture. And Stefan, you asked me to talk about let's say cultural buildings, etc. And I thought, given what Biden has announced yesterday, that I want to focus my lecture today mainly on this topic. So the question really about sustainability and how climate change is potentially going to change our built environment. So that's the question we need to ask ourselves every day in our work, but also in our research. So I can jump over this. Stefan already introduced the company. I have the privileged situation that I also have this professorship at the Technical University in Munich, where I have a chair of something like 25-ish people doing research only. And I think it's interesting for me. I feel really privileged that I'm able to work as a practitioner and as a university professor doing education, but also research at the university. Now, we talk a lot about sustainability. What does sustainability mean? I think that's a very important question. We found this picture in a magazine where they said, welcome to the breathtaking Tokyo water park, where you can wash away the pressure and stress of the overcrowded city. We found it really nice, but I think we do one big mistake in all our efficiency, particularly efficiency considerations and discussions. When we talk about energy efficiency, we always talk about, in the United States, kilobtu per square foot and year. So there is no relation to people. There is no relation to how people enjoy the space, how many people use the space. We can design a zero energy building. If nobody's using it, it's a waste of resources still. So we can't disconnect this question of sustainability from the question of architecture quality, of, let's say, environmental quality. We need to design spaces for people, and people have to use it. And we also know that buildings people don't like very much are going to get teared down very early. So by definition, this can't be sustainable. So that's why we love to work on this interface of design and environmental quality and spaces, try to inform architecture to design spaces for people. Therefore, we need to understand how people perceive space, how people perceive environmental quality, which is something sometimes very difficult. We call it climate engineering. And just to give you an idea what climate engineering could mean, in 2010, we got invited to do an installation at the Architecture Biennale in Venice. And usually our work is dealing with the invisible qualities of space, with temperature, etc. However, people go to a biennale to see something. So you want to see an object. And so we had this idea to do an indoor cloud, let's say an artificial cloud, because a cloud for us was, let's say, that we climate engineer the environment to the extent that a cloud starts to appear and become visible. In order to do a cloud, you need to have a layer of saturated air with 100% humidity. Sorry that I'm using SI units here, but I'm going to translate it for you in Fahrenheit. So you need to have a layer of something like 80-ish, 85 degree Fahrenheit with 100% humidity. And when you have saturated air, then you can spray in water and the water particles do not evaporate and it starts to appear as a cloud. And so warm, humid air has a lower density than cold, dry air. So we know cold air is going down. So this layer has a lower density and it's going to float on a dry, colder layer below. But then we need to prevent the cloud layer to touch the ceiling, because as soon as it touches the ceiling, we do get condensation at the ceiling. So we need another hard layer with something like 90 or between 95 and 100 degrees, but dry air above. And with these two layers, we squeeze this cloud layer in between. So you see, it's engineering, it's climate engineering. And then Tetsuo Kondo, an architect from Japan, he designed the space, he designed the ramp where people could walk through the cloud and really experience the different climate conditions. And here you see the cloud from below, and this is the cloud from above. So it's just an example to what extent we can really manipulate climate conditions in a very short distance, and to what extent we could use this knowledge also to provide comfort locally and not condition buildings, big spaces everywhere. Of course, this is not our core business, doing clouds. Usually we try to avoid getting clouds in buildings. Now I could talk about all these amazing projects with amazing architects we could work on. We had the pleasure and the honor really to work over the past almost 30 years, which was an amazing experience. But let me focus on this. I think it was amazing when Biden yesterday announced that the United States want to reduce carbon emissions by 2030 by 50%. And that the next decade will be decisive. That's a short period. 10 years is nothing for the building sector. And like Stefan said, the building sector is kind of key. It's key. It's key because it has, from all sectors, it has the highest contribution to our carbon emissions. But not only this, also our building sector is also responsible for a certain amount of carbon emissions that comes from the industry, like say material production, but also the way we design cities, let's say our urban design planning, is contributing significantly also to commuting. So density, urban sprawl, etc. So it's not only building design, it's urban design, and altogether is decisive of how we design how the environment in which people live. So it's a very high responsibility, and we know that this request or this requirement of reducing carbon emission by 50% is going to change our built environment. The question is how, and how can we design it? And I'm trained as an engineer, but from my point of view, it's less of an engineering task and more of a design task. And I'm going to show you a couple of reasons why. So this is the request. This is what's required. Our CO2 emissions from the building stock have to become zero sooner or later. In Europe, the European Union, has the EU carbon roadmap, which states that the building stock has to become basically carbon neutral by 2050. This is what we see over the past 20 years talking about sustainability. People apply gadgets on something which is stupid to begin with. So this doesn't make any sense. I think we cannot be successful by just applying gadgets. We cannot just apply technology. We need to rethink the whole thing. And we have to become efficient by design. So I want to show you a building just as an introduction, and then go into latest research and how we translate it in some of the newer projects we worked on. So this is a building we already completed in 2010, where we worked with KPMG architects from Toronto. And I show you this because when we worked on this building, Manitoba Hydro, the client, requested that this should become the most energy efficient high-rise building in North America. So this was the task that was established by the client. And then we looked into the climate conditions. So we did some climate analysis, understanding the climate conditions there. And we found that in winter, it gets down to temperatures of minus 35 degrees. And at this point, it's about the same in Fahrenheit. Temperatures you've probably never perceived, never certainly never seen in Vegas. But it's cold, it's very cold. And they have temperature half a year below freezing, below 32 degrees. But then what was interesting, people always said, yeah, it's getting cold in Winnipeg, but whenever it's cold, it's always sunny. So we thought, let's have a look deeper, more thoroughly into solar radiation data. And we found that the city of Winnipeg has almost as much solar radiation than the city of Rome in Europe. More than the city of Milan, more than any location we have in Germany. And then we looked at how much solar radiation do we get on a vertical south facade. And we saw that we even get more in wintertime than we get in summertime. So we figured out that if there is a place on this planet to do passive solar design, it's actually Winnipeg. So this became a driver for the whole design. And we ended up with a tower, an 18-story tower on a 3-story podium. And the tower, we separated into 3 6-story packages. And we use this south-facing winter garden we have as a buffer zone. We use to precondition the fresh air. So fresh air enters into the winter garden. The winter garden is the lung of the building. And then we have water features for humidification, and then we take the air from the winter garden and distribute it by a raised floor plenum into the depth of the floor plate, take it out on the north side, put it down into the basement where we have a heat recovery unit, bring the heat from the exhaust air back into the system, and then we have radiant tubing in the concrete slab for heating purposes. We have a geothermal system under the building with almost 300 boreholes going down 400 feet deep, providing something like 50% of the heating demand for the building and 100% of the cooling demand in summer. And so in summertime, we cool the slabs by the geothermal system. We open up the south facade from the winter garden so that we basically have outdoor conditions. And then since we don't need heat recovery, we exhaust naturally by this solar chimney. So the idea of a solar chimney is only, let's say if you have a warm air want to go up, but for this kind of buoyancy effect, you need to have height and temperature difference. It's a function of height and temperature difference. The height is a given, but when we have like 25 degrees outside, or let's say 78 degrees outside, 78 degrees inside, then there is no temperature difference. That's why this chimney is glazed on the top so that the sun then continues to overheat the exhaust air to keep this buoyancy effect, the natural ventilation going. This is why we call it solar chimney. And then this is the south atria, how it looks like. You see here on the backside, the water feature, which we need in wintertime for humidification purposes. On the right side, these benches, under those benches are the supply air units, which provide the air for the whole 6 stories into this winter garden zone where it picks up the sun, warmed up by the sun. We condition this space in wintertime only to 50 Fahrenheit. Everything else is done by the sun. And then we take the warmed air by units which are behind those panels and distribute it by a raised floor plenum into the office space. This is the mechanical room of the building. It's all integrated. There is no air handling room in this building, no mechanical room for air handling units in this building. It's all integral to this south-facing winter garden, which is like you see 3 times in this building, in the high-rise, and a smaller one in the podium. And then to the east and to the west, we do have a double facade. We do have a shading device, a retractable shading device in the double facade so that it's protected against the wind. But the shading device also, like a Venetian blind, outside the conditioned environment here. So then we have the radiant cooling coming from the ceiling, from the slab, the displacement ventilation, if we operate on mechanical ventilation coming from below, but then people can open the window, and in certain periods a year, about a third of the year, we totally turn off mechanical system and operate the whole building just on natural ventilation. So you see this high adaptivity of this facade systems, of the overall building, of how buffer zones like wrapped around the building, combined with openings, combined with retractable shading devices, how they all contribute to a passive hybrid, mechanically hybridized climate control system and strategy. What does this all mean in terms of energy? So what you see here, MNECB was the building code when we designed the building. So it was requested that we design the building for a number somewhere below 260 kilowatt hours per square meter in a year. On the left side, this is typical Canadian commercial buildings. And the 88 kilowatt hours was what we have predicted or projected in design with our modeling. So you see it's a significantly lower. And then when we started to operate the building after a couple of years, here first the good news, in terms of complaints, that was a surprise for us. Manitoba Hydro did this kind of post-occupancy evaluation, comparing the building to other buildings they operate. And in the 3rd year of operation already, we had only 50% amount of complaints for too hot or too cold in this building. Despite the fact that we condition it with the concrete slab, it's like a system which is so slow reacting that if someone complains that it's too hot or too cold, it takes about 24 hours to correct the temperature by something like 2 degrees. So it's such slow reacting that there's basically no control. And compared to a fully air-conditioned building where people can go to a thermostat and say, I want to have 72 degrees now, and then an air conditioner kicks in, compared to such a building, we have half as many complaints. Very interesting. Good point for research. And then every workplace is exposed to daylight. We have, which became interesting now in COVID times, we have 100% outside air, no recirculating air in this whole building. And so overall, we have 1.25 less sick days measured compared to their other more typical North American buildings. So that's the good news. So people obviously appreciate the environment, appreciate the daylight, the natural ventilation, the radiant cooling, and not the drafty, noisy, typical air conditioning systems. Now the bad news, we also looked at energy, and the first year of operation when we had full data was in September of 2010. And the previous year, we ended up with a number which was almost 100% higher of what we have projected. And then it was October 2010, November 2010, and so on. And it took us 2 years of fine-tuning, of monitoring to get to what we have predicted. 2 years. And you see here, there was a jump In the first year, we had some issues with an hydronic system. We couldn't really use the geothermal heating system really well. And so there needed to be done some adjustments. But everything else was only fine-tuning controls, sensors which are a little wrong, or lighting which turns on too early, all these kind of things. So it was not the one thing, it was like 100 things. And you need to find them. You need to spend time. You need to look into the BMS, into the building management system, and fine-tune and find all of these things in order to get to the building operation. So we call this performance gaps. So something we got really concerned about. This is the building after completion. This is the solar chimney on the north side, the entrance to the building. Of course, we became really proud that something that contributes to the operation of the building got also the signature of the building, or became part of the signature of the building. But this performance gap was kind of with us, and we looked into it. We thought, are our buildings too complicated with this high adaptivity of shading devices that go down, operable windows that open up, etc., etc.? Is it too complicated? Also, this like hybridized approach between passive and active. So we looked into literature, did some literature research, and we found this study done by the Royal Institute of British Architects, and it's called Better Spaces for Learning. And in this study, they looked at almost 60,000 school buildings all over Europe, and they figured out that 95% did not perform as intended. 95%. So we recognized it's not just us, it's totally normal. It's totally normal that we design buildings which do not work as designed, and we just accept it. And then we found another study in Germany and figured out that typical office buildings do have an average performance gap of 70%. 70%. We accept. We always blame the automotive industries that the cars are using more gas than what they advertise. But we are not better. We are worse. So just recently, someone in a public discussion said the building industry pretty soon is going to have their Volkswagen moment. I think we are there yet. Given the pressure that comes now with what Biden announced yesterday, it will come now. We're going to have our Volkswagen moment now, and we have to become serious about this. So what we recognized, we developed these models on these highly adaptive facades. We showed that in extreme climates, not only in cold climates, also in hot climates, we showed that we can do smart buildings, even if they are highly glazed. They can be very efficient. They provide good comfort. They have this kind of adaptivity. But this is what we see. And also the building in Canada, we have completed in 2010, 10 years ago. Except for ourselves, almost nobody in North America tried to copy the model. This is in Dubai. We still see these stupid glass buildings, no operable windows, all glass, no shading devices, no nothing, deep floor plates, people disconnected from the facade, so much coating on glass so that the glass is dealing with the solar radiation that people even get good daylight inside. They don't even get white light. If they look outside these buildings, the grass over there is not even green. So if you look at color rendering index, it's a shame. So we have to, it's kind of annoying. So this is, let's say, international style. But the model we have developed, we showed that it can be successful. But we also recognized when we need 2 years to get it to operation, it's not a robust model. So as a first hypothesis for tonight, I have to state that this glass architecture has failed as a model in terms of robustness and sustainability. That's what we need to state. I don't want to say that Manitoba Hydro has failed. We did tons of buildings which work beautifully, which are great, which are amazing. but it's not a role model. If you just think about how many engineers you need to design those, how many engineers you need to operate those buildings. So we need to have something more robust. So we recognize this is not really a robust model, and robustness is important. We can't deal with this performance gap. So the idea of robustness is not only that we have robust materials. The idea of robustness is that we have an overall system which, let's say, when we have uncertain boundary conditions, an uncertain boundary condition can be people, can also be climate change. So we have these uncertainties, and so these uncertainties, those deltas, should not lead to an overall system that fails, should not have a big impact on the overall result in terms of environmental quality and in terms of energy use. This is the definition of robustness. And so therefore, we always talked over decades, we talked about high tech and low tech, and we never found a definition. And so suddenly with robustness, we have, let's say, a methodology we can use to really test how robust the system is. Like the Manitoba Hydro system, when we tested in our modeling with a shading device that failed, and an operable window that doesn't open, then we suddenly recognize the space overheats. So we need to have this kind of stress tests to see how robust an overall system becomes. And that's why we love to talk about this, because let's say, again, high tech and low tech, there is no real definition of what it means. At the university, we worked on 2 books. And I want to quickly show you some results of one book, which was another aha moment for me personally. So this is a book about schools. Unfortunately, those books are published only in German. I'm very sorry for this. But we did this book on schools where we compared 12 schools together with the chair of Florian Nagler. And the bottom right school here is a pure timber building, massive timber building, designed by Florian himself. Florian Nagler is an architect from Munich, and is also a colleague at the university in Munich. But we looked at buildings from different periods, and we started with a building from Theodor Fischer, who was a very important architect in Germany in the early 20th century. And he designed this school building here to the left, upper left side. Which was completed in 1898, so 120 years ago. And then a building from the modernism in Amsterdam, some buildings from the 50s, 60s, say this one from Günter Behnisch in Göppingen, and then 80s, some of them already renovated. And then a couple of newer buildings from 2000, here from 2000, basically 2008, 2011, those 2, let's say Recklinghausen here, this one, and Erding, this one, are designed as passive house schools without operable windows. And then this timber building. I don't want to go through the details, but we asked the photographer to go there to take pictures in every building from the same position. So we have pictures from every classroom, which was quite interesting, from every corridor, and even from the mechanical rooms. And then we did measurements. And so you see here a 5-minute measurement during occupation time from each building, looking at outdoor temperature on the left side, an indoor temperature on the left side over outdoor temperature, and you see the comfort band. And don't worry, I'm not going to go into the details. I'm not going to explain you every single number. But we also looked at CO2 concentration, so on air quality. Some of the buildings do have mechanical systems with cooling. Some of the buildings have mechanical system for ventilation. Some of the buildings are purely natural ventilated and have no mechanical cooling. What we figured out is that the building of Theodor Fischer, which was completed 120 years ago, which is like, the space is 4 meters tall, which is like 12 feet tall. And it has 800 square foot instead of 600 square foot, what we do today. And we do something like 9 feet tall today. This one has, 12 feet. So much more volume per kid sitting in there. So what we figured out is that from all buildings with which were naturally ventilated, the artificial building had the best air quality, which is kind of understandable because we have twice as much air volume in this building per person sitting in there. But also from all buildings without mechanical cooling, it had the best thermal comfort in summer. Given the 62 feet thick brick walls the building has, also partition walls 1.5 feet thick. So the thermal mass led to the fact that this building has the best thermal comfort in summer from all buildings without mechanical cooling. But not only this, it has these tall windows, and because of these tall windows with the lowest fenestration ratio, we get the most even distribution of daylight because those windows are taller because the space is taller, and so daylight falls deep into the space. And the last thing we figured out is that without any acoustical absorption at the ceiling or somewhere, we also had about the best acoustical performance. Just because for glare control, or for daylight control, they do have these big curtains, and it's so much fabric since the space is so tall that we get enough acoustical absorption to have really good reverberation time over the different frequencies in this space. So today in research, we would call this multi-objective optimization. And now coming back to Aravena, his quote, at the time, 120 years ago, this was common sense. And this is what we have lost. You see here the mechanical rooms of the buildings. In the Theodor Fischer building, we have a boiler room of something like 300 square foot. In the timber building of Florian Nagler, which is supposed to be, let's say, high-end energy efficient in terms of all the mechanical, high-tech, high-end mechanical systems. They had to build a gym under the building to house all the mechanical systems needed. All the mechanical systems needed to achieve an energy efficiency, which is never there because of performance gap. To achieve an environmental quality, which we have lost because we lost this idea of architecture. We lost the floor to ceiling height. We squeeze people in much smaller spaces. And then we try to overcome this loss of environmental quality with mechanical systems. And then we save space above ground in order to build it below ground. This is stupid. This has a level of stupidity, what we are doing. So this is, I don't want to talk about style here. I don't want to talk about that we have to go back and do buildings like 120 years ago. It's like this understanding of environmental quality, what's spatial quality, and get this back into architecture, get it back into design, and not try to solve everything with mechanical systems. And we are so impressed that we started a research project also with Florian Nagler, many chairs, many professors involved from the Technical University. We called it Einfach bauen, build simple. So we have to get some simplicity back into design and solve things by design and not by systems. And we said like a couple of goals, like no composites. We do walls as one material. So that was a premise. So we had a couple of premises when we started, but we also said we have to get rid of layers. And just we did designed or looked into a parametric study where we looked at pure concrete, insulating concrete, compared to what we do today in Germany or in Europe. Most likely also in North America, even though it's not so common to build concrete buildings in North America. But there would be a concrete wall, and then in front of it, there would be a layer of insulation with a plaster on top of it, some shading devices for the window below. And then inside, we always have this kind of insulation in Germany. And on top, we have a concrete layer, a screed, we call it, a floating screed for acoustical purposes, but also because we put all the installation in there. And I said, like, let's get rid of all of this. So we need to design like Theodor Fischer. Then we don't need a shading device. We use insulating concrete, so then we don't need have outdoor insulation. We put all the installation, make it visible, put it on top of the walls. Then we don't need this floating screed. And so the same principles we developed, mainly Florian Nagler, his chair, also for timber. How can we design a timber building, reducing the amount of layers with brick? And then we found a developer who were interested, but we also did this kind of parametric study on room level. And we wanted to prove that building height is essential, room height, floor to ceiling height, that if we increase floor to ceiling height, we can get the narrow windows that are tall so that we get daylight deep into the space. We get a very even daylight distribution. But by doing this, we get lower fenestration ratio and then get rid of shading devices. And so we ended up with 81 geometries, 4 orientation, 3 different building materials, 3 different glass types. So we studied something like almost 4,000 options and basically tried to prove Theodor Fischer, try to prove common sense of 120 years ago. And then we looked at uncertain boundary conditions on top to test how robust the overall system is. And again, I don't want to go into the details, but as a final result, what we figured out is that the brick building here, for instance, compared to a passive house over a 100-year life cycle, has, even though we designed those buildings to minimum energy standard in Germany, we said, forget about energy efficiency. We don't go beyond minimum energy standard. And then over 100 years, we are, for a normal user, so the dotted line here represents the normal user, we are better or almost the same than a passive house. The timber building obviously is much better because it has less embodied carbon because of materials sequestration of timber in the building construction. So we found that this is much more robust. Even though we have a higher energy consumption on day one, over 100 years, we have a better performance than all of these, let's say, super high-end buildings, not even considering performance gap. And then we found this developer in Bad Aibling, B&O Group, who were interested in this research, and they said, come on, I'm gonna build you 3 of these buildings. And now these got highly published now all over Germany, because I think also of the aesthetics. I was impressed that we do all these research projects which end up in a report. Nobody cares about these reports. But as soon as you build something, all of a sudden, it's published everywhere. But what you see these arch-type windows here in the concrete building. So this is the concrete building on the left side. The middle one is the timber. On the right side, it's the brick building. And those arches we have because we said no composites, pure material, no mix of materials. So there's no reinforcement in this concrete. And even when you have no steel in concrete, you can't have a beam. So that's why we ended up with these arch-type windows. With timber, of course, you can have a beam, but also with masonry, we said no beams here. The bricklayer had to lay down this arch so that we don't need any beam, any steel and concrete in this brick structure, so that we keep it all pure, one material. And now we are in a phase where we design 3 buildings for student housing, a total of 200 rooms. And now you see the roof system, the roof structure. So we said as a next step, we have to become carbon neutral or zero energy, however we want to call it. And then we looked at how much energy do we need to generate, and if we put photovoltaic on the roof. And then I went to Florian and said, we need bigger roofs. We need to generate more power. And therefore he started to design these overhangs. And he said, like, it's kind of interesting because through modernism, we got rid of these overhangs. And now all of a sudden, because of solar energy, we get it back into design as, let's say, a kind of a design methodology. Here you see the idea again using space height. This is a picture into the model. The spaces here are also something like 10, 11 feet tall. And so the bed is on top of the bathroom so that we get taller, but also more narrow. Here again, this is a model picture. You see the bed on top of the bathroom. So this is in design, and I hope we start construction this year. Again, picture from the model. You see the extended roofs, creating this overhang to get more solar energy generated on the roofs. So we always have this debate of minimizing material due to embodied carbon. And just for fun, I looked up how much embodied carbon do we put into 1 square meter. So 10 square foot of wall assembly. And if we have a double facade, floor to ceiling height, then you see that even though it's always considered lightweight, the highest embodied carbon we do have in a glass facade, like the Manitoba Hydro facade. If we use concrete and external styrofoam insulation, this is concrete wall, then a brick wall, sorry that it's named here in German. And then this insulating brick is better. But then as soon as we get to clay and timber as, let's say, mineral timber for insulation, then all of a sudden it can become negative. So that's the potential. So there is no straight correlation between the amount of material we use, the kilograms we use, and the embodied carbon. So this in mind, we worked with Haas-Cook-Zemrich on the headquarter of the Alnatura. Alnatura is a supermarket chain for organic food. And of course, they wanted to have a very sustainable building. And so we ended up with a rammed earth wall. Material was supposed to come from the site. There were some difficulties. I'm not going into this. This will be a lecture in itself. But there is a company in Austria called Lehmton Erde, Martin Rauch. They industrialized this, let's say, production of clay walls. And here you see we put in foam glass, mineral material for insulation purposes. We embedded in the wall assembly. And then we also put in piping for heating and cooling purposes, so that the walls are a radiant source for heating and cooling. And so he created these kind of wall assemblies and put it into a warehouse close to the building site and dried them during construction time. And then when, let's say, the superstructure was ready, he had his cherry picker brought piece by piece on site. Here again, you see the piping for heating and cooling purposes. And this is how it looks like now. This is the space. It's all open. It has a, let's say, it's really low tech. We reduce mechanical system to a high degree, trying to take advantage of clay. And the beauty of clay is that it has a lot of thermal mass. So a lot of thermal mass that is providing temperature control, passive temperature control. But it's also still the best material, or among the best material, for a hygroscopic control of space, so humidity control of an indoor environment. It's a beautiful material. It's available everywhere. You can get it for free. And then we also, this is the second book I showed you. We did some measurements again, and here you see, let's say, indoor humidity in wintertime and outdoor humidity in red. You see where it gets way too dry outdoor. We could keep the indoor humidity always in a comfortable layer. And now again, talking about the pandemic, when we are exposed to dry air, which is an issue in cold climates like Winnipeg, but also in Central Europe. But it's also an issue resulting from air conditioners, air conditioner dry air. And in a dry environment, people are much more sensitive to pick up some sort of bacteria in their immune system through the lungs. Again, a couple of images of the building, how the building looks like, has been completed about 2 years ago. And so it leads me to the second hypothesis, that massive buildings per se are more robust. However, this doesn't necessarily lead to more embodied carbon. I think that's the major message. I want to finish and show a few slides. I'll go over it very quickly. Talk too long so far. Talking about outdoor comfort, urban microclimate. I know in Vegas, you're in a desert climate, but we see climate change changing also our climates in our cities, and mainly in our cities. That's why we also have to address climate, not only in an indoor environment, but also in an outdoor environment. And we did an exhibition last year in Berlin. And the basis of the exhibition was a study that got published, and here you see the source on the bottom, which showed the delta in temperature that is expected in our cities worldwide. And we recognized that the highest delta, among the highest delta, we see in Central Europe. So central cities in Central Europe are going to see the biggest temperature difference, as well as Vegas is probably this one. So I know Vegas is also considering incredible climate change because it's always combined with urban heat island effect. And the urban heat island effect particularly is a problem at nighttime when the cities heat up and stay hot in the night. In Vegas, it's an energy issue. People don't stay as much outside. That's a problem. And it causes more energy consumption, which can be significant for air conditioners. In Europe, it's an issue because in housing, we don't even have air conditioners. So that's why in hot periods, we see a higher mortality rate. People die. In the summer of 2003, we saw an increased mortality rate in France of 40,000 people. We do research about this at the university where we do so-called climate walks. You see here, we did this climate walk in Berlin, where we see the relationship between urban morphology and perceived temperature of people. So you see the blue line here, there was a walk in Berlin. You see the blue line indicating the air temperature, but the line below indicating the perceived temperature. So you see that even if the air temperature doesn't change so much, the perceived temperature can be very different. And so we did this in this exhibition, comparing Berlin to Rome, because this is what Berlin is going to face, similar climate condition than Rome is having today. But Rome is designed for this climate, is designed for having this climate in mind. And we don't even need to do any modeling to know that this alley in Rome behaves much better in hot periods than this street at the bottom here. So on the left side, you see the GSW building from Sauerbruch-Hatten. So that's the third hypothesis. If I go back, this is even more beautiful. So we can easily imagine sitting here in a hot period. We don't want to sit here when it's really hot and sticky. So we see that the transformation of the built environment towards climate adaptation provides also great opportunities. I mean, that's the basic message. Why do we fear change? The opportunities are much higher than the risks, but it's a design task. And with this, I want to show you the Place de la République, where we worked with TVK architects and Martha Schwartz on a redesign of Place de la République in France with Transolar. And you see, this is how Place de la République has looked before the transformation, dark tarmac, heating up, making it unbearable, but also see traffic, and it's almost impossible to get onto Place de la République without getting killed by some cars. And this is after the renovation, after the redesign of Place de la République, just changing the layout of the material, different materiality, evaporative cooling, trees, etc. And then this is how it looks like. So it's, you see how people enjoy it. It's delight. So it's not a burden, this transformation. It's an opportunity. Thank you very much.
Thank you, Thomas. This was exciting, very good. You raised so many points, and I'm getting here a lot of questions coming in for you. And it's so interesting. I mean, you had also some provocative points. You're challenging us architects, and you will know 95% of people online, 100 of people online here are architects and AIA members, but you say you can solve things by design, which is fantastic. It's very optimistic viewpoint. So thank you for giving us, reminding us, challenging us, and giving us the power. So it's not an engineering task per se. It is has a lot to do with common sense. 120 years ago, we knew it, but then we lost it. And you spoke about when architects made rooms simply higher, 3-4 feet higher, which meant that windows could be taller, and there could be all kinds of side effects of that, like the bigger curtains and the more daylight and so on. So it's very interesting. You also spoke about the performance gap, which you very frank and open said is many engineers say it's going to be like this, and it's not, as something we can talk about, I believe. But also your attitude of back to basics, which is so different from some engineers tell us we have to build a machine, we have to make complicated solutions and put more and more technology in, whereas you say the other way, we only put in technology that is really necessary. And you reminded us that in Las Vegas, half the year, we can probably run a large number of buildings without air conditioning. But the air conditioning keeps running all year long. It's a design task. And to bring in daylight and fresh air and to do what you've done in Winnipeg, for instance, very interesting. But we must remember, Las Vegas is the fastest warming city in the entire North American and in the nation. So we are warming by far faster than any other city. And that's why we have this excessive urban heat island issue here already. And that's something, there's a question on that here that we want to talk about. So first, maybe to get started, one question is the research process in your office. Obviously, a lot of research is needed and more research, and this combination of being at the university and running a global firm is very fruitful and very helpful. There's a cross-fertilization between the practice you do and consulting architects, but also the research you do with your team of 25 researchers. So that's fantastic. But also PhD students being the engine room of that research often, and in the center, in the chair. How much time is spent on research for each project, and how do you develop the research question is somebody asking here. And also, is the client willing to pay for the research?
I mean, let's put it this way. I mean, at Transolar, we have this beautiful situation that we get only asked by clients who come with a certain ambition. So that's the starting point.
Yeah,
that's a beautiful situation for us. And so therefore, let's say the total fee basically is a kind of R&D. But at the same time, I'm always also critical about what is research. What is research and what is innovation? It's a tricky question, and there's a fine line in between. However, for me, what's very important for research is that we publish it, and it needs some critical reflection. And that's something we not often do in projects. So that's something we also have to bear in mind. That's something we have to learn as practitioners. It only becomes research when we put it in context, when we critically reflect it, and when we publish and talk about it. Otherwise, it's innovation. It's not research. But this kind of systematic research which a PhD student is doing is not something that we can invoice to a client. So of course, when we work on building design, it's much more pragmatic. So you're already in this debate in the design team, but also with the client. The design already goes into a certain direction. And so you don't research it systematically. We don't look at 4,000 options like we did for Einfach Bauen when we work on a real project. So it's a more straightforward and more pragmatic. And this way we kind of can tailor our process, our design process, and how we support the design team with our work. We can tailor it to make it affordable for the client, but the client has to pay for it, of course.
Yeah, thanks for that. That's interesting. And then you made yourself a name. So architects that want to do the most sustainable building in the country come to you, which is interesting. And it leads us to a question Sam is asking here. He's asking, he says, the approach of the 19th century building is great. Less is more. We are now more toward poorly designed buildings with much technologies. Okay, yeah. So question, shouldn't those sustainable solutions that you provided have been noticed by the designers themselves? Why is it that they need you? And why don't they seem to know that? It probably goes back to designers that have been in business for a long time, the architectural education here, and so on. Do you want to comment on that? Why the designers don't seem to know it themselves?
Yeah, I don't know. Maybe someone from China applied at the Technical University in Munich, and I talked to her why she want to come to Munich. And she said, like, there's this sentence in this saying in China, if you want to see the mountain, you have to stay aside. And so you can't see it if you're on top of it. And so that's why she loves, she said she loves Chinese architecture, but in order to understand it, she has to go abroad. I found this very interesting. Maybe it requires this view from outside to really understand it. But I have to say, it also took me 25 years it was an aha moment when we studied, when Florian Nagler came up with the idea that we include this 120-year-old building. And by the way, I forgot to mention that in 120 years, there was no major renovation in this building. That I thought, why should we look at such a building? And then it was an aha moment when we see how it performed. I don't want to blame anybody. I think what we all, when I look back, I mean, coming from Stuttgart, Stuttgart has always this kind of lightweight glass tradition. Stuttgart school. This is how I got socialized in design and in architectural design. And when I look back at our early years in Transolar in the 90s, this kind of glass architecture, this adaptive facades, that had been modern. When someone came with brick, you thought like, come on guy, get over it. Here, this is the new world. And I think the experience of the last 25 years made me think about it. However, I don't want to say again, and that's really important for me. I don't think this from an aesthetic point of view. I don't want us to design buildings like we have to design them 120 years ago. I want us to understand the physical relationships of space and get this know-how back into design. I also don't want, I know Vegas is getting super hot in summer. I don't want to blame anybody for operating an air conditioner. I think maybe a radiant system like Manitoba Hydro would be more comfortable, but anyway. But we should think of building systems as being supplemental. And not being dependent on mechanical systems. We should think of buildings that work by itself by design, and we add mechanical systems supplemental to a passive design approach. When we just rethink this approach, then there's nothing wrong of having some sort of air conditioning system.
Interesting. And of course, you mentioned the urban heat island, which we will discuss a little bit more in a minute. Here is a question from Luca Caruso. He says, how can we as architects explain the concept of performance gap to the client who expects to receive the best perfect service possible and will not be able to accept the performance gap, especially if the engineer is reluctant to describe it? Do you think that an honest, frank debate with the client will be a good selling point or could be dangerous? Any comment?
Yeah, I mean, I know that particularly in North America, it's kind of considered weird when someone talks about, let's say, the failure of the own work. However, I think we should get this honesty into the debate, indeed. And there is a lot of research that had been done. I think it's probably easiest to just show different research and different publications on performance gap also in North America. I know that the state of New York, I think, requests that all energy numbers of public buildings are published. And so out of these numbers, a lot of people looked into it. I know that the Green Building Council looked into it and to see whether lead silver, lead gold, lead platinum buildings perform better than others. And so out of these studies, we see that the United States do have the same problem with performance gap. I think there is published enough that it does not need to be related to the own work.
Yeah, and that's why we have scientific peer review, which then qualifies it further even. The problem here, of course, in North America and increasingly in Europe is to get sued as an architect if the building overheats. Very common problem. So let's talk more about this mind-boggling, overwhelming situation, how much we waste energy, water, but also materials in the process of construction. And you mentioned longevity and durability. Simply to make things last longer is, embodied in your concept of robustness, interesting term. But what does a robust system look like exactly? And how can we measure robustness? And you said low tech. What exactly is then the role of technology? You as Transolar, you still perform highly sophisticated computational simulations for concept validation. So let's elaborate a little bit more, if that's okay, Thomas.
Yeah,
please.
sure.
The interesting term of robustness, longevity. What is a robust system? What are the characteristics, and how can we measure robustness?
I mean, let's say, first of all, we still do these kind of Manitoba hydro buildings. And I said, let's say the system, the building has not failed. I just question whether it's a role model, that we can roll out. It seems to be too complex. It seems not to provide enough robustness. The definition of robustness is, again, with the uncertain boundary conditions, first of all. And that uncertain boundary conditions do not have a big impact. So let's simplify it. It doesn't matter if you have operable windows and the user. We also today, we want to give the user influence over his own environment. And so if you have a stupid user, the most stupid user, the building should still perform okay. So that's the request of robustness, whatever that means. But what you say about longevity, what it looks like, these are all difficult questions. I do not have answers yet. I'm happy that we do have a methodology to test it. And when you have a big performance gap, then by definition, it's not robust. It can't be robust. Otherwise, there would not be this big performance gap. I don't want to say it's doing a 2 feet thick brick wall, but we see that thermal mass helps. We see that these kind of materials which provide a hygroscopic climate control, which is, by the way, also timber, provides better environments. So I think there is not the solution, but if we use it as a driver, I think it can help us to come up with a new approach of design, away from this all glass.
Yeah, I think it's important for cities like Las Vegas or Phoenix or Dubai, even a better understanding of the role of thermal mass and how it can play into our advantage. But then, of course, there is the danger that it stores solar gain during the day and then radiates it off in the evening at nighttime. And you mentioned urban heat island being a nighttime issue. So the question is, air-conditioned glass buildings in a desert city like Las Vegas, Phoenix, Dubai, we're still building them. And you mentioned Aravena in Chile speaks a lot about this issue for a long time. And so it's not only the solar heat gain that leads to overheating. The urban heat island effect in cities like Las Vegas or Phoenix or El Paso is immense. So you've shown us what you've done at the square in Paris. You changed black asphalt to white material surface and many other things. You planted large leaf trees that can help. Trees are always good, tree planting, but trees need a lot of water. They're very thirsty, especially if you plant palm trees that are not native here, like we do here. So we're creating another problem of water scarcity in the desert. We are here in the desert, and we definitely have not oversupply of water. Water is always a scarcity. So what could work for a city like Las Vegas to reduce the urban heat island effect? Give us a couple of examples.
I mean, it's hard to change the urban morphology of an existing city. However, I want to just disagree that thermal mass exposed into the public realm is a disadvantage. We did measurements in medieval cities. We could show that the old part of Genoa behaves really well, has the lowest urban heat island effect. The city of Siena in Italy, they claim that they do have a negative urban heat island effect, that it's colder in the city without any trees, without any vegetation, just by the material they use, by the urban morphology, and that it's colder in the city than it is outside the city. I have no scientific proof for this, but that's what the city of Siena claims. And it can certainly be true. What you see in this upper image, this is Rome. Thermal mass can be very helpful to also control climate in the public realm, but you have to shade it. It should not heat up. It should not be exposed to the sun for a longer period of time. So here you see a little sun exposure before sunset, but the street here is so narrow that it's not exposed to the sun the entire day. And then it cools down at nighttime and keeps the public realm, let's say, reasonable during daytime. So it's a question of sun exposure. And as I said, you can't change the fabric, the urban morphology of Vegas. But let's learn from southern Spain, Seville. They do have these fabric shading devices on top of the streets. As soon as I think the point we start to understand is that we can only control microclimate in our city by redesigning the public realm. And then we get into a renegotiation of space, whether we use it for car infrastructure or for other purposes. But as soon as we get rid of cars, or as soon as we have less cars, we have all kinds of possibilities with shading devices, etc., to really rethink our public realm and do climate adaptation.
Yeah, very interesting. Shade is everything, especially here in the hot desert climate. And we did a lot of research. We did a comparative study between Australian cities and Shimban in Yemen, and the self-shading of narrow laneways. We looked at that and we published on that peer-reviewed several papers over the last 20 years. So I think it's interesting because you confirm architects can have a huge impact by doing projects at the urban scale, thinking about the public space network, redesigning the public space and the challenges of the public space, providing shade structures, and of course, re-greening the city, renaturing the city. The European Union has a big research agenda called nature-based solutions, where I think 500 million euro have been invested already to identify the best practice of nature-based solutions. And also small interventions, for instance, to improve, they can add up to a lot, small interventions to improve and upgrade the existing building stock that is poorly in terms of energy efficiency. But let's come back to that key question for us here in Vegas, if I may, and I know we have another 10 minutes maybe, but urban density questions. Of course, we must stop the sprawl, and therefore we must have an efficient growth boundary. We cannot allow the city footprint to expand any further. But we are very good in doing that here. You know, another suburb gets rolled out. At the moment, Las Vegas grows by 10,000 people a month. Every month, we have 10,000 more people here. It's absolutely mind-boggling. And we are one of the 3 fastest growing cities, despite COVID, again in the US. So how can we stop sprawl, and what kind of urban densities do we want? How to transform the car-dependent US city, Las Vegas? You know, and when is higher density acceptable and a good idea? Because there's a lot of resistance and there are a lot of reasons against it. You know, you have this interplay between, if you increase the density, is the danger that you increase the urban heat island effect. So you have to do it in the right way, in a smart way. Density that also creates more space for urban greenery, which sounds like a contradiction, but it can be done. We've seen examples. And also good public transport. If you want to get people out of your car, of the car, you have to offer very good public transport. Otherwise, why would they wait 2 hours for the bus, or there is no subway system? So talk a little bit to us, please, about what can we do in the Southwest. And this is not just Vegas, it's also Phoenix. And, you know, we have 30 million people, 40 million people living in this situation here in desert cities around the Southwest that have the urban heat island impact. Talk to us about it, please, Thomas.
Yeah, I mean, let's say, not talking about what people want or people desires, just considering it. I mean, that's the beauty sometimes being an engineer. You can reduce it down to a couple of numbers. But this idea of a single family home, let's say the American dream, is certainly not a good idea for a sustainable living. I mean, that's something we know. I think Paris framed it really well. Mayor Hidalgo, she said, we have to redesign Paris as a 15-minute city. I'm sure you heard about this. So every inhabitant of Paris should reach everything needed for the daily life, work, school, shopping, everything within 15 minutes without a car. So if we take this as a metric, then we end up with density. And I would disagree that there is no necessary correlation between density and urban heat island effect. There can be a correlation, but if we design it right, like the street we see here from Rome, there must not be a correlation. The opposite can actually be the case. Density can be a chance to control urban heat island effect much better. And so when we worked with Foster on Master City, we ended up on a very dense city, but you end up with a dense city like here if there are no cars. So if we design streets for cars, temperature goes up immediately. And that was the struggle. That was probably among us one of the problems why the project did not get built as designed. I don't want to talk about failure, but they changed the design from this point. But the idea was that all kind of people movement happens below a platform, so that we get the cars out of the city, and getting the cars out of the city, we can create this kind of compactness, this kind of self-shading, etc., etc. We know that the courtyard building, the dense courtyard building, like we see it in Andalusia, works really well in this kind of hot climate. We get daylight from the courtyard. We don't need to get it necessarily from the narrow street. So I think we know all the solution if we design new cities. The question we need to ask ourselves, and you need to ask ourselves in Vegas, when you grow by 10,000 people, will you put those people, do you want to put those people into single family homes? Is there a new plot for urban sprawl? Or should there be, let's say, should we think the city more as what we call it, the multiple center city, so that we don't design people where people just sleep, cities where districts where people just sleep, or do we design parts of a city, urban city? What makes urbanism? And I think we should get away of this idea of a single family home.
Yeah, so we need a polycentric city.
A polycentric,
as urban structure, which is embedded in the 15-minute city. I call it the city of short distances.
Yeah.
And I call it density without high-rise towers. Our research shows that the soft spot is between 4 and 8 story height, where you can have the most energy efficient city with a block structure, like we see many cities are very successful. So I think Masdar was necessary. You know, the new plan in Abu Dhabi, of course, it didn't get built at the end the way it was perceived, but it was a necessary project. It cost a fortune to get there, and they failed in the upscaling of the ideas. At the end, when you go there now, it's more like a business place. Nobody wants to live out there next to the airport. I think they did a lot of mistakes. I spoke to the Sheikh many years ago before anything started, when they came up with the idea, and I said, don't do that. Especially not in this location, building into the desert a new town. What you should instead do, you should upgrade and qualify the existing Abu Dhabi, which is a terrible, 20 years ago, it was a terrible place, a windy place, you know, with car parking lots and air-conditioned glass boxes. And don't go out there at the wrong place.
That's what I always said. I always said, like, we don't need carbon neutral Masdar, we need carbon neutral Abu Dhabi.
Yeah, so redesign and upgrade the existing city that is already there is always a much more sustainable strategy, of course. But Masdar was necessary at that time for us. Last question, if I may, that came in here. It's about the cost of photovoltaic. Somebody's asking. The cost of photovoltaic systems has come so much down now, while the efficiency at the same time went up. Is there any prognosis you can make? For instance, will buildings and cities become decentralized power stations where the city and the building is producing more energy than it needs?
I mean, the first question is it necessary that the building? My concern is always when this is, let's say, the premise, when this is the hypothesis that every building needs to produce more energy than it needs, then we end up again with single-family homes, or with something like 3-story buildings. Let's say I tell students at the university, we need to think about solar integration in every building we design. If we design buildings today without solar integration, it's a mistake. It's a design mistake. Because that will become the norm. I think we have states now here in Germany that consider requesting a solar installation for every new building by code. So this is something that's going to come. However, the point I still struggle with solar integration in buildings, and particularly in dense cities, is, first of all, by density, we will, just given the density, we will not be able to cover 100% of the energy consumption. And it's also, let's say, also when we talk about urban farming, we will never be able in a dense city to produce all the food we need in the city. A city is always dependent on its surrounding. Why should we make it independent in terms of energy? And solar panels also contribute to the urban heat island effect. I think that's something we also have to admit and have to see. Now, the question is, we are right now working in Saudi Arabia on NEOM. They are talking about having a PV installation in the desert of something like 25 by 25 kilometers. And it became so cheap when you put it in the desert that no other source of energy can even compete. No coal, no gas, no nuclear, nothing can compete against PV power, particularly in such a sunny place. But why should we make the difficulty and bring it into the city when you can just lay it into a desert? I think we should discuss this more as a kind of social or a society, more like a society question. And the debate we started in Austria now with some Austrian architects, with Delogan Meisel architects from Vienna, is that they say when we come into our old villages, it looks awful having all this like patchwork of panels on the roofs, which like, so can't we find other solutions? And we started to do a study and so like, let's make it again a design task. It's space planning. It's a task of space planning. It's a planning issue. It's not an engineering issue. It's a planning issue. Let's establish how many square kilometers do we need, and then we see where it can go. And so together with Delogan Meisel, now we worked on a couple of designs of where we could put PV nobody have even thought about yet. And it's again an investment in infrastructure where we can tap into and creating synergies so that we can create also public shading structures. I mean, it's the easiest in Vegas, where you can create a synergy for other use. But maybe also we talk about greenhouses in Saudi Arabia, which we can cover with PV and creating and also grow food. And so there's a whole lot of ideas of how we can create synergies and combinations.
Yeah, very, very exciting. And here is a study waiting for you when you come to visit me very soon in Vegas, where we want to do the zero emission casino and the zero emission strip, where we redefine how those buildings, what those buildings look like, how they perform, and how they get their energy decarbonized. And therefore, we have a lot of space behind the mountain in the desert, not far from the city at all, where we can have a very large solar field powering. We could run the entire city of Las Vegas on solar power, so much sun radiation. We have equal amount of sun radiation than in Saudi Arabia. So what you plan for NEOM would equally apply here. And this is coming. It just needs the first big developer, the CSAR, MGM, WIN, and so on, SANS. Who's going to be the first? Who's going to be brave enough to go out and say, I have a casino that uses daylight and that has almost no air condition, only in the very peak summer months, and is actually producing more energy than it needs. And the energy needs for a casino are immense because you've got a hotel and all those things. So we're gonna need to work together on making Las Vegas more compact, more walkable, and more mixed use.
We have to get back to learning from Vegas.
Yeah, learning from Vegas, but differently. Not
differently,
about
the new one.
Billboard, which was exciting in 1972. Now, 50 years later, next year, it's 50 years ago that Learning from Las Vegas was published. And we should now re-coin the notion of learning how to make Las Vegas green. And I think that's a wonderful way.
You should do a new book, calling it now the new Learning from Vegas.
Yeah, it's been
Learning from Vegas 2.0.
Yeah, so wonderful to talk to you about all those questions today. And I'm sorry, I know there now came a couple of other questions in the meantime, but we are kind of out of time. And you were very generous, and thank you very much for a wonderful presentation. We recorded, and the hope is that all the recordings of those wonderful presentations by Zaha Hadid, by Renzo Piano, by Snow Hetta, which we had over the last weeks, and yours also, Thomas, will soon be up on the YouTube channel of the American Institute of Architects for everybody to enjoy as a resource to go back and to study and to better understand all those important concepts like robustness and low tech and back to basics. We wish you a very nice evening. It must be something like 10:30 p.m. at your end now. I know you had opened a nice glass of wine earlier.
Yeah. We already had a birthday party of a friend tonight, a virtual birthday party on Zoom.
Very soon we're going to be together again, face to face. So thank you very much from the AIA and the School of Architecture here in Nevada, in Las Vegas. And we wish you all the best. And thank you everybody for listening in to our exciting lecture series. This was the final talk.